Okay, now we'll see about the different loads acting on beams. Loads act on a structure causing it to undergo internal stresses and displacements, which the structure should be able to withstand satisfactorily, meeting the requirements of strength, stability, and serviceability. So the loading on a structure may take any one of the following forms. Direct actions, it may be in the form of forces and moments, and indirect actions due to support displacement, constructional errors, and environmental changes. Okay, the most common source of loading is by direct actions, meaning forces or moments applied directly on a structure. These loads may be caused by the action of gravity, the natural environment, or other sources. So what are the forces due to nature? They are dead loads due to self-weight of the structure, live loads due to human occupancy, storage, vehicular traffic, etc. Wind loads due to aerodynamic forces of wind, snow loads due to snow accumulating on top of the structure, earthquake loads or seismic loads due to the movement of Earth's crust, inertial forces induced on the structure vibrating due to ground motions, soil pressure due to the bearing pressures under footings and lateral pressures on retaining walls which retain the soil, impact loads caused by vehicular traffic on bridges, roads, railway lines, etc. Water pressures in water storage structures such as water tanks and dams, wave loads on offshore structures and ships, and blast loads due to explosion. Most of the above loads, except the first one, that is the dead loads, are difficult to quantify because they are random in nature and both temporarily, that is in time, and spatially, that is in space. It varies with time and space, so it is difficult to quantify it. So building codes often prescribe the magnitudes of the loads to be assumed on the basis of statistical data available and acceptable risk of exceedance. The distributions of loads are also idealized for convenience in the form of equivalent loads, like we are taking it as uniformly distributed loads or linearly varying loads, such that they will generally result in safe designs. Loads which are dynamic in nature are often replaced by equivalent static loads for convenience in structural analysis. We are taking it like that. The static loads are multiplied by an impact factor or dynamic magnification factor to account for the maximum amplified response due to dynamic effects due to earthquakes, wind loads, etc. So the direct actions or the directly applied external loads can be taken into the following forms, into two forms, like concentrated or distributed forces and concentrated or distributed moments. We can take the direct loads into two types, concentrated forces or distributed forces, and concentrated moments and distributed moments. Concentrated forces, usually expressed in the unit kilonewton, and are idealized point loads. In actual practice, a load is applied not on a single point but by bearing over an area. When this loaded area is relatively small in comparison to the total area available, this approximation provides a convenient simplification which is usually safe. For accurate results, however, the force may be modeled as a distributed load. Now, do you know which is the example for a distributed load? Self-weight is a simple example of a load which can be taken as uniformly distributed throughout the volume of a homogeneous material. So we will take it as a uniformly distributed load. Self-weight is usually taken as a uniformly distributed load. Now an example for a uniformly varying load is hydrostatic pressure acting on the sides of a water tank, which have a linearly varying distribution with a zero value at the water surface and the largest value at the base. Now concentrated moments. This will cause bending, and these are commonly encountered in continuous beams and frame elements at the rigid joint locations owing to the moment resistant capability of the rigid or the fixed joints. Now in the case of a rigidly connected beam slab joint, the wall slab junction will be subjected to distributed bending moments. When a slab is considered in isolation, the distributed moments at the boundaries are treated as externally applied loads. Now concentrated torques are usually encountered in shafts. For example, the torque applied while turning a screwdriver. It is an example of a concentrated torque. Now an eccentrically applied torque example is the effect of a sunshade on a supporting lintel beam. So the direct actions on a structure or structural element induces internal force resultants and support reactions. So under the static conditions, the resulting system of forces along with the externally applied loads must satisfy the conditions of static equilibrium. So considering the free body of the entire structure freed from the support constraints, the support reactions must equilibrate with the direct actions, that is the direct loads. Now if you consider a part of the structure, the exposed internal forces must be in equilibrium with the direct loads and the support reactions that act on the cut-free body. So the direct loads along with the support reactions can be also regarded as the external forces. Now we'll see what are the internal forces or what are the internal forces. The internal forces are bending moment, shear force and axial forces. So the concentrated loads, we are usually taking it like that. This W, a point load acting at a point. Uniformly distributed, you will usually represent it like this. W per meter acting for a distance x. So you have to take it as a constant. You can take it either as a concentrated load W into x acting at the center of this loaded span, or it is a uniformly varying load like this, a triangular load or a trapezoidal load. So here you can take it as W per meter as the maximum ordinate. So the total load will be half into area, that is area of this triangle, that is half into W into x, where W is the maximum ordinate of this triangular load. Okay. So what are the indirect loading? It is possible that a force response as well as a displacement response may be induced in a structure without being caused by externally applied direct loads. We may use the term indirect loading to refer to the cause of such load effects. Usually this type of loading occurs in addition to direct actions. Okay. And if this is not anticipated in the design, it may result in serious consequences. So a structural engineer should be able to analyze the response caused by such indirect loading. So it should be noted that even in the absence of direct actions, internal forces, what are the internal forces? Bending moments, shear force and axial forces, and support reactions can exist in a condition of static equilibrium. So the sources of such indirect static loading may be support displacements, that is due to settlement of the supports or rotational slips of the supports, or due to constructional errors due to accidental eccentricities and lack of fit, and also environmental changes, that is changes due to temperature, changes due to shrinkage, and also changes due to creep effects. So support settlement means we are usually designing the support to be immovable, but they will move, and as a result this produces structural response. Now second one is constructional errors. Errors in construction may introduce a force response in the structure, and these errors may take the form of accidental eccentricities in loading or lack of fit in trusses. So errors due to environmental changes are the changes that occur in structural elements due to temperature variations, due to shrinkage, and also due to creep. So when we are designing a structure, we have to consider all these things which may encounter due to the changes in environment or due to constructional errors. So the environmental changes require small changes in geometry in the structural elements, and this has to be accounted in the design of structures.